Welcome to the Explainer. Today, we're going to pull back the curtain on the one simple secret that runs pretty much every single electronic device you own. Let's dive right in. Okay, that sounds totally backwards, right? I mean, how can 10,000 volts be less dangerous than just 1 amp? Well, the answer gets to the very heart of what electricity is, and, believe it or not, our own biology. You see, our bodies are running on these tiny little electrical signals all the time. And it's the flow of outside electricity, the current, that messes everything up. To really get this, we've got to understand the difference between the push and the flow. And to do that, we need to meet the three main characters in the story of, well, every single circuit out there. Let's call them the electrical trinity. You've got voltage, current, and resistance. All right, first up, voltage. The easiest way to wrap your head around this one, just think pressure. It's the force, the electrical push that gets everything moving in the first place. Without any voltage, the electrons are just, well, they're just sitting there, not going anywhere. Okay, so if voltage is the push, then our next character, current, is the actual flow of electrons. It's how many electrons are actually moving past a certain point in the wire. And like we hinted at the beginning, this is the part you really have to watch out for. This is what makes electricity so dangerous. And last but not least, we have resistance. Think of this as the friction or the squeeze in the system. It's whatever is trying to slow that current down. Imagine water flowing through a pipe. Resistance is like a narrow section of that pipe. It makes it harder for the water to get through. And get this, everything, even the wire itself, has at least a little bit of resistance. So we've got a push, a flow, and a squeeze. But how do they all work together? What's the relationship? Well, that's where this beautiful little golden rule comes in, and it's called Ohm's law. Yeah, so way back in the 1820s, this German physicist, George Ohm, had this big realization. He figured out that these three things, the push, the flow, and the squeeze, they weren't just random. Nope. They were all connected by this incredibly simple and elegant math equation. And that discovery, it pretty much became the foundation for all of modern electrical engineering. And here it is. This is the whole shebang. V equals I times R. Voltage equals current times resistance. It's so simple, but it's the key to everything. It tells you that the amount of push you have is a direct result of how much flow you've got and how much squeeze is pushing back. And you know what's so cool about this law? It's super flexible. If you remember a little bit of your high school algebra, you can just move the pieces around to solve for any of the three. If you know any two of them, you can always figure out the third. It's like the ultimate cheat sheet for electricity. Speaking of that squeeze, sometimes you need to control it very precisely in a circuit. And that's exactly what this little guy, a resistor, is for. You see those little colored bands on it? That's not just for decoration. It's actually a code that tells you its exact resistance value. Super clever, right? It lets you dial in the exact amount of squeeze you need. Okay, so we've got the rule down. But what happens when you start building things? Does the way you lay out a circuit actually matter? Oh, absolutely. It all comes down to whether the current has just one path to follow or many. And that brings us to the two fundamental ways you can build a circuit: series and parallel. So check this out. On the left, you've got a series circuit. Everything's just in one big line, one single loop. On the right, that's a parallel circuit with all these different branches. Now here is the crucial kind of weird thing to remember. In a series circuit, if you add another resistor, you make it harder for the current to flow. The total resistance goes up. But in a parallel circuit, if you add another resistor, you're actually adding a whole new path, which makes it easier for the total current to flow. So the total resistance actually goes down. I know it sounds weird. Let's use an analogy to make it make sense. Okay, for a series circuit, just picture a single-lane highway with a bunch of toll booths. Every single car, that's our current, has to go through every single toll booth. Each one of those toll booths is like a resistor, slowing everything down. So what happens if you add another toll booth? Well, the whole line of traffic gets even slower, right? The total resistance goes up. Simple. Now for parallel circuits. This is where it gets cool. Instead of a highway, imagine a ski slope. You're at the top, and you want to get to the bottom. Each trail down the mountain is a different path, a different branch in our circuit. Now, if the ski resort opens up a new trail, does that make it harder for people to get down? No way! It gives them another option. It makes it easier for more skiers to get down the mountain at the same time. By adding more paths, or resistors in parallel, you actually make it easier for the total current to flow. The overall resistance of the mountain goes down. All right, this is all fantastic theory, but let's get real. How does any of this apply to, say, the outlet in your wall? It's time to connect Ohm's law to the real world and talk about the actual power that runs our lives. So whenever you look at a light bulb or a microwave and you see how many watts it uses, you're looking at its power. And a watt is really just a measure of energy over time. It's how much electrical juice that device is using every single second. And hey, would you look at that? It's another beautifully simple formula. Power equals voltage times current. That's it. To figure out how much power something is using, you just multiply the push by the flow. It's that easy. So why should you care about this? Well, think about a standard wall outlet here in the US. It gives you 120 volts, and it's usually on a circuit breaker that's rated for 15 amps. So let's do the math. 120 volts times 15 amps, that gives us 1,800 watts. And that number is super important. That is the absolute maximum amount of power you can safely pull from that one circuit before you start running into trouble. So let's do a quick reality check. Imagine you've got a power strip plugged into that outlet. You plug in a 900-watt microwave, and then you plug in a big 1,100-watt space heater. Is that a good idea? Well, let's see. 900 plus 1,100 equals 2,000 watts. That is way over our 1,800-watt safety limit. You're trying to pull too much current, the circuit's going to overload, and pop. Hopefully your circuit breaker does its job and trips before anything worse happens. And hey, here's one last really important tip, especially if you ever travel internationally. You have to know the difference between an adapter and a converter. An adapter just changes the shape of the plug so it fits in the wall. That's it. A converter, on the other hand, actually changes the voltage. And this is critical because if you take your 120-volt hairdryer from the US and plug it into a 240-volt outlet in Europe with just a simple adapter, you're going to send way too much voltage into it and poof, it'll be fried instantly. It's a mistake you only make once. So you see, from the tiniest little resistor on a circuit board to the massive power grid that lights up our entire country, it all comes down to that simple, elegant dance between the push, the flow, and the squeeze. It's all just Ohm's law. So now that you know the rules of the game, what are you going to see when you look at the electronics all around you?